So in this video, we're going to talk about real gases. So this is what happens when gases don't behave ideally. And so the conditions under which you might see this would be things like at higher pressure and lower temperature, right? Because our ideal gas conditions were low pressure and high temperature. So now we're high pressure, low temperature. The ideal gas behavior can break down. So even at conditions of STP, we do see some deviations from ideal behavior. So if you remember, at standard temperature and pressure, an ideal gas would have a molar volume of 22.41 liters per mole. So under these same conditions, here are some sample molar volumes. So H2 is 22.42 liters per mole. That's pretty close. Helium is 22.41. That's very nice. N2 is 22.40. NH3 is also 22.40. Carbon dioxide is 22.31, so slightly bigger deviation there. And then something like Cl2 is 22.06 liters per mole. So the effect on the molar volume and ideal behavior, this behavior is affected by two factors. And those two factors are particle size and intermolecular forces. So we have not yet gone into intermolecular forces. It is a topic that we cover in second semester. But I am going to give you a brief introduction here since it affects our gas behavior. So intermolecular forces are attractive forces felt between molecules. It makes our low temperature collisions not elastic. We sometimes talk about this in terms of stickiness. So if the collisions are not elastic, so we lose some energy in that collision, or maybe the particles are kind of sticky and they stick to each other rather than doing that perfect bounce off that we're assuming is happening under ideal conditions, we start to see effects in whatever values we want to calculate. Usually pressure or volume is what we're looking to calculate. So if the intermolecular forces are strong, I'm going to abbreviate this IMF, we would say the molecules are stickier and deviate more from ideal behavior. So the deviation from ideal behavior, I'm just going to give you the van der Waals equation, which is the equation that we use to calculate whichever factor we happen to need. And it's going to look like we took the ideal gas law and then just kind of stuck some weird variables in there, which is exactly what we did. We have part of it that corrects for how big the particles are, and then we have a part of it that corrects for how sticky they are. So one variable will be related to how big the molecule is, and the other one will be related to how sticky it is. So this is the van der Waals equation. That we use for real gases. And it is, in brackets, pressure plus A, which is one of our variables, times N over V squared. And the brackets, start some new ones, times V minus N times B, which is our other variable. And this is equal to N times R times T. So each gas will have a characteristic A and B value. Let me put a box around this equation really quickly. So P, V, N, R, and T are all the variables that we have dealt with for the ideal gas law. So I'm not going to list them out next to the equation here. But I do want to say a little bit more about A and B. So each gas has characteristic A and B values. So this means that when you need these values, you're going to have to go look them up in a table. I am going to give you a few in this video, but I want to say what they relate to. So B values scale with molecular volume. So this is the factor that is taking into account the size of the particle in the equation. A values scale with the strengths of the intermolecular forces. And just to relate this to one thing that we did do this semester, that is going to depend on the types of bonds in the molecule and the overall geometry of that molecule. So just a couple of examples. I don't have the B values listed here, but just some examples of the A values that will show up. And the units on A are atmospheres times liters squared divided by moles squared, which seems very weird, but if you look at where it is in the equation, after you multiply it by the factors it's next to, you're going to get atmospheres out of it. This factor is going to correct the pressure in the van der Waals equation. So something like SO2 has 6.71 for A, H2O has 5.46, CO2 3.59, and then let's just go down to something like helium, which we saw was behaving pretty close to ideally based on our molar volume at STP, right? The correct effector here is 0.034. So whatever is going on in helium, right, it's not affecting this pressure very much, which is why we see behavior that's very close to ideal behavior.